Thanks a lot for joining. So this session is about Essentia.js and music information retrieval with Essentia.js. And we'll try to give you some brief introduction to music information retrieval. You can see the slides for this session here by this URL. In the materials for this tutorial, you should be able to have these slides as well. The PDF. So it should be on the website, in the description of the workshop. You will have a link to the GitHub repository we created that contains links to these slides. So you could go with us through the slides, and whenever we click, you can also click, and this way it's easily accessible. And we added some references, some links to these slides for your future reference in the future. So if you miss something, don't worry. If you can't assist the entire workshop, don't worry as well. You can just have a look of some of it and then look the rest later on. So I guess we had to present ourselves. Maybe Albin can say a few words.
Hi everyone, I'm Albin. I'm a research collaborator at MTG. Actually, I was at MTG when we started this project. And currently I'm working as a senior ML engineer at MIR. It is a music streaming service from Denmark, focus on AI curated playlists, etc. And I'm also one of the main developer of the JavaScript part of Essentia. Yeah, Dmitry, you want to introduce?
Yeah. Yes, so I'm a senior researcher at the Music Technology Group, Universitat Pompeu Fabra in Barcelona here, and I'm also the lead developer of Essentia, the original code that we ported for Essentia.js. I'm the maintainer of that code.
Yep. Hello, everyone. My name is Jorge, and I also work at MTG with all these guys. And I am currently a researcher and developer working on some applications of Essentia.js and Essentia.js models as well, which we'll have a look at today.
Hi, I'm Luis, and I'm a PhD candidate at the MTG, and I'm also a research scientist working at SonoSuite, and I collaborate with Essentia.js.
Excellent. And you can know more about our group, our research group, if you visit our website, which is below here. Just type in Music Technology Group and you probably already know about some of the work we do. We sometimes participated in, and some of our previous members are active in this conference. So we are very happy to be here. And today, so we will cover Essentia.js for music information retrieval. So this is just an outline of the presentation. So I'll just skip through this. But basically, we will start from what is MIR, how we did Essentia.js, how we could run a Hello World application. We'll do with you the first application. Then we'll show some demos. Then we'll talk about deep learning inference, a little bit more on what we already presented today in our paper. Some demos, some more demos. We will show an industrial use case as well from Luis, because he's working in a company that is a music distributor, and they want to use this type of technology for their use cases. So he will discuss that. And then we will have some QA and playground session if time allows. But at any moment in time, feel free to stop us, ask questions, so that it is more like a discussion, and we just go through that step by step. So I'll start with a generic introduction to MIR, and I guess it may be overly generic. So I wonder what is the percent of the audience? How many of you know about music information retrieval? Well, or either know or even actively participate. So if you can put some likes or whatever, I don't know if we can measure this here in the chat. But I will assume that a very generic introduction is fine, no, everyone. So starting from the audio analysis, well, actually, Wikipedia says that audio analysis is extraction of information and meaning from audio signals. So information and meaning for analysis, classification, storage, and retrieval and synthesis. Retrieval is a large part traditionally with information retrieval. Now the history of the concept of data sets, retrieving multimedia objects from data sets. So MIR started in that retrieval context. And I guess that's why it's called that way. No, music information retrieval. There was an attempt to rename it to music information research. So MIR the same. So is the same, but I mean, retrieval is more narrow than research, and I like the research as well in the definition. So we're just researching any information about music, and it can be related to audio. It can be related to metadata as well, right? So the conference that we have, that is already for over 20 years, International Society for Music Information Retrieval. You can visit the website and see, get familiar with it. It's very interesting, very inspiring, large, diverse community of people. So they define MIR as processing, searching, organizing, accessing music-related data. Well, Wikipedia states that it's interdisciplinary science. So you would meet, for example, a musicologist together with maybe web audio developer, together with some machine learning professional on the same conference. So, and that's a great thing about it. So it's like a melting pot where a lot of things can cross, and a lot of the research is based on audio. So we have a lot of people from audio background, audio engineering background. There is a few music information retrieval tutorials on this conference that have been done before. So you can just check those links if you are interested. There's just a generic overview of some of the typical tasks. You can click on those. And also importantly, even though we talk about music information retrieval, even if in the title of this workshop, right? Well, in general, what we talk about applies to sound in general. So we don't like you to think that this is only about music. I think many of the things that can be done with Essentia.js, or maybe things that you want to do, they're not necessarily related to music, but to sounds and audio in general. So we could talk about sound analysis in general. And some of the examples of the tasks that we work on are, well, one of the common popular ones in MIR is to actually browse large music collections, music corpus, data sets, personal music collections, etc. And a lot of works have been thinking about that we can analyze audio and extract some useful description, something that a musicologist can talk about, but also that's feasible for a machine to extract, maybe something lower level, and use those features, those characteristics then to visualize music collections, organize music, maybe query by similarity and things like that. Also, you could imagine different types of interfaces that can be done. So the concept is, well, traditionally music search was limited to metadata, to like artist name, genre. We want the systems to be able to analyze audio and bring us some novel ways to find similar music or unsimilar. And for example, in free sound, we use that. So we have query by example approach here. For any sound in free sound, you can click on similar sounds and it will output you the most similar sounds. And that similarity is based on audio. So in particular, in fact, it uses Essentia features. We also use it in music recommendation. Sound and music classification is an important part of this type of music and sound characterization, right? So on the left, you see, for example, an ontology by audio set. So this is a categorization of different sounds into semantic categories that they proposed, and many researchers work with this taxonomy, and they try to build algorithms that can predict these things for a sound. On the right, you see our platform called acousticbrains.org, where people can submit their music. They extract a specific software on their computer, analyzing music, and they submit results to a server. And here you can see you have some predictions by different classifiers, some machine learning algorithms, and they say some probabilities of what they believe this song is. You can also see, well, actually, no, that's it, more or less. So semantic tag-based retrieval is very important nowadays, right? So you can use it to search for music, for example, in production music libraries. It's a common thing in Jamendo, which is a corpus, a large collection of Creative Commons music. They have a way to browse by instruments, genres, themes, and notes. Imagine you can do that automatically in this type of analysis. So in Freesound, you can browse by tags as well. You can browse by combination by tags. We still do not have functionality to classify by audio these tags, but we have people working on that. So it's in the future. Another typical example of what many people actually want from music analysis, well, commonly wanted thing is key and tempo estimation. Maybe not surprisingly, there's, for example, this database of music where DJs can upload their tracks and they can estimate key and BPM so they can use it when they play music in their DJ sessions. Music source separation, of course, is very interesting as well. Automatic music transcription. So here we could align, we can extract music information in terms of notes, events from the audio itself. That's another direction in research. Music identification and cover sound identification also. Well, here basically everyone, I guess, knows Shazam. Everyone used that. So audio fingerprints and furthermore trying to understand if some sound, the audio is a different version of a music track is a more challenging task that we work on nowadays in music information retrieval. And of course, a lot of things can be used in music and sound production. For example, on the left, there's a loop mesh that used actually our software before it was open sourced. They use some features, well, basically MFCCs, I think something else probably as well, to build a sound similarity. And then you can play with loops. On the right, you see a classical visualization like Winamp style, the old school. I would like to see some visual art that is using audio features. And I think that's an interesting intersection with video art and so on, can be explored. But basically, to summarize, in a lot of tasks, what we need are sound and music features, and they can be pretty low level, they can be mid-level. We can start with something basic and objective like loudness, go up to some complex things like melodies, onset position and times, rhythm, BPM, going up to even subjective domains and semantic descriptors that not necessarily people will agree, but within certain applications, they can have sense. For example, you could talk about music genres, different emotions evoked by music, instrumentation, danceability. These concepts are very useful. They could be more hard to work with because they are somewhat subjective, and that's what we work with because we work with machine learning a lot. So nowadays we often work with these high-level semantic descriptors starting from low level. Essentia is a software that we work on in our group, and we have published it to open source in 2013. Maybe some of you have used it. Well, I see some people in the chat, I think they used it. So thanks for using, thanks for all the support. Basically, this is a collection of algorithms that are designed to be reusable and optimized for computational speed. It was written in C++, so it's really fast. We use it through Python bindings though, because if you want to prototype, it's a good way now to be able to prototype with Python. All this functionality that we can do nowadays with it is amazing. So we have the C++ backend and the Python bindings. And on top of that, people did some different bindings as well. So it is cross-platform. People used it for mobile platforms as well. For real-time applications to a certain extent, depending on the algorithm, because we have many. Some of them are pretty, can be used in real time. Right, so there's over 260 algorithms, well, I guess you can just click here, and in our documentation, you have algorithm reference where you can read through that description. But yes, so now we have algorithms for audio input output, DSP, sound and music descriptors. As I mentioned, like all this stuff that we work on with MIR, many PhD theses were implemented into the software. And we also implemented functionalities for machine learning inference, which is what we have right in the case of TensorFlow and models. So one interesting thing is that it's modular, as I said. So you as a user, you are responsible to design your own complex chains of computations that you want to do. For example, we have an algorithm that maybe contains hundreds of others. It's called music extractor. It kind of computes everything you may need that we thought is useful. We use it in Acoustic Brains project. And basically inside is like this kind of a network of algorithms connected together in a data flow manner. You can think of that. So you can say the input audio, we will pass it to a frame cutter. It's like a typical pipeline to compute a key, to estimate key of a musical key. So from the audio, we compute, we cut short segments of audio. Those frames are then passed to windowing. That is just the intermediate algorithm to compute spectra. From that spectra of that frame, we can find the peaks of that spectra, right? So we'll have some predominant frequencies. Those frequencies actually fall into some semitones. Now we could do a mapping. So we do that with HPCP, which is Harmonic Pitch Class Profile algorithm. And basically the output of HPCP summarizes the distribution of energies across 12 semitones, let's say, summarized across octaves. And that then the key algorithm accumulates this type of information through the entire audio, so through all the frames. And then once the track is over, it does averaging and computes key estimation. The key estimation is done by, you can imagine, like after averaging, we have like an overall distribution of energy in different semitones. And you can have, as you imagine, C major would have a typical shape for within certain genres that we could match against. So we look at the form of the shape of the distribution, and then we can predict the key. So this is kind of the basics of how it works. But basically, the idea is that you yourself can do a lot of things by modifying each step, parameterizing each step. But if you don't want to worry, you just need the key, you can run the composite algorithm that we provide for that, key extractor that just outputs key based on the audio. But if you really want, to tune it for your specific type of music, etc., you can go inside, you can do it all.
Just a brief note, we will be building that pipeline to build a core detector in a few minutes. So yeah, it's good to have that as a reference.
Okay, so there are many applications in MIR of the library. I'm very happy to see that used also outside of MIR. And just a few examples that I think are interesting. So the first one, I found that it was used for cough detection in audio analysis for medical applications. So nowadays, unfortunately, with all these pandemics, it's very relevant, right? So it's nice to see that it gets some uses in this medical applications. On the other side, I also saw one application that were using Essentia descriptors to analyze, I think it was like a forest or something, where they were measuring biodiversity. So by sound, they can understand what type of animals are living or what time of the day they're active or something like that. And so it is a little bit more generic. We have some applications outside of MIR, and maybe in web audio, there's a lot of applications that are completely outside of MIR, I'm sure. And so I think it can be still useful. We have different applications covered in the library, but basically I think we covered some of them already before, and you can check this later. So for music and audio analysis on the web, what about this? So there are some of course there is web analysis, web audio analysis, right? So there are systems, there are web platforms you can open and that they run audio analysis, but very often they do that on the server. So the reason is because first, there is not enough software to do that on the client. In fact, a very limited amount. Second, the web audio API capabilities are somewhat limited for audio analysis as well. This is just a growing area. We're all excited to see now that through the past years, there is a lot of new possibilities. There are also new possibilities to port libraries to JavaScript and WebAssembly. Right, but basically there's a lack of software libraries on client. Here are 3 examples server side and 3 examples on the client. So the server side are just the APIs. So you may know some of them. Free Sound, our collection of sounds, contains an API that runs Essentia. So through the API, you can access Essentia features. So the features are pre-computed when the sound is uploaded, actually. MIR is a library for audio analysis, purely written in JS. I guess maybe someone used. If anyone used, please let us know. So we found also that there is a conversion, JS conversion for lib extract from C, and also similar for Obio. Obio is another C library with some features. Audio features that also has limited JS conversion. Well, we found the repository on GitHub. Probably we missed something else. Let us know if there is something else. For sure, there may be something that we missed. But basically, even taking MIR, which is probably contains the largest amount of features among the 3. Well, in Essentia, we have much more algorithms. So we thought that it would be nice to try to port them to JS. We knew that we could do well, mscript and cross compilation, but then now recently we finally set on this task, and Albin was working on that in the past year, porting the library. And I think Albin can start explaining that.
Thanks, Dmitry. Can you see my screen?
Yes, we can.
Okay, perfect. So yeah, as Dmitry mentioned, so we worked on porting this library to JavaScript, seeing all the latest development in the web audio ecosystem, and also the existence of WebAssembly support across browsers, so we can easily cross-compile native code to run in JavaScript. And this is not a new thing, but we saw that there's a growing momentum of support of tool chains to do it much easier. And we also want to make these algorithms available to run on the web. So we presented the library last year during the MIR conference, as Dmitry mentioned, the International Society for Music Information Retrieval. So we presented the library last year, and this was the very first version of the library. And after that, we made some improvements. And you can check the landing page or website and the repos and examples on this link. And if you also want to know more about the technical details, you can also check the paper. But anyway, I'm going to go through more high-level details of the library, and then we can go on to some hands-on thing, as Jorge mentioned before. And again, please stop me if you didn't understand something, or if I wasn't clear explaining it. Please put in the chat, or yeah. And also, you want to mention the license of the library, and it's licensed in AGPL version 3 because the Essentia, our mother library, is also in AGPL license. So we need to have the same license. And you can check these links to know what does it imply for your JavaScript projects. And also, you want to mention that it's also available under commercial license under request. So maybe before getting into the technical details, let's check out how this library works in a browser, right? So if you want to get an overview of it, maybe Jorge, you wanna walk through some demos?
Yeah, let's do that. I'll share my screen briefly. Yeah. Okay, so can you see my screen, everyone?
Yes.
Yes.
And you can hear me correctly, I assume, but let me just check that the input to the browser is what it needs to be. So yeah, so here we have some examples of real use cases of Essentia.js. And I'll go through the real-time ones because they're, they're exciting, and also more visual. So this is a MEL spectrogram example. So on the x-axis we've got time, and the y-axis will have MEL bands. So it's a spectral representation. In this case, we have 96 MEL bands. So that goes from low to high in frequency spectrum. And yeah, let's just try it. So this is me speaking. You can see that has a certain shape. If I whistle, or if I just click my fingers, I don't know, if I play the guitarlele, it will have a. So you can sort of see the harmonics. So that's a very simple example, but also we have other things like more, let's say, mid-level, like Dmitry was explaining. So perhaps pitch. You might want to know what pitch a certain tone is. So here, the y-axis on the left, we have pitch in hertz, but then we also have it by pitch class on the right. So that would be what note in the 12-tone equal tempered system it corresponds to. And same thing in the x-axis, we've got time. So let's try this with a bit of a different. Let's just start the microphone. This should be a G. A B flat. Okay, so that's a kind of simple pitch example. I'm guessing everything sounds right. Everyone can hear me, right? I'm not just.
Yes.
Okay, cool. And yeah, let's have a look at some other stuff. So, for example, related to pitch, but more closer to perhaps chords. Analyzing chords would be HPCP chroma. So this is circle of fifths. Well, no, it's not really circle of fifths, but it resembles a circle of fifths. If we play any group of notes now, so let's play a C major, we should see all three notes activated. So. Or a G minor. Whatever, in D minor. That's a bit more complicated, right? There's more interference, but the point is it can detect multiple notes at the same time, right? And then also very recently, we've been working on an onsets demo. So this required the use of some custom extractors, which I think Luis will talk more about later. But basically, the idea is that Essentia.js is extensible, as Dmitry said, and you can always go into our templates, C++ templates, and create your own custom pipeline, being confident that it will be kind of fast enough. One of the things that we had to kind of wrap around was onsets because of the types that we're using between C++ and JS. They had to be kind of wrapped. And that's why I made some extractors for this. But this is a simple onset detection demo. I've loaded here, I think, a base. And this is using a complex onset detection function. So that's the sort of the function that we've computed and fed to the onset detector. There's multiple functions that you can use. And this is work in progress. Like there's a reworking of the interface in progress. And of course, that's with everything that at least I present today. Feel free, everyone, to make any comments and to, if you make any suggestions or have any ideas of how it could be improved, super welcome. So, but yeah, so this is bass sound, which might be a bit loud. It is for me, at least. So there we have a bit of a glitch or some the pick on a string that was captured. And the point of having multiple onset detection functions is that you would have, they behave differently. So this HFC, you could also combine them and give them different weights. But for sake of the demo, let's use the high frequency content one. That should focus more on high frequency stuff, obviously. let's have an acoustic drums file. And so it should grab very well like the hi-hats and any kind of transient. So for example, that's a kick and a cymbal, it sounds like. That would be the snare drum, right? So that's another example of perhaps MIR in the web. These tend to combine multiple metrics. So complex will use the spectrum, so the complex spectrum, will use both the magnitude. So differences, correct me if I'm wrong, Dmitry, but it uses differences in magnitude and the spectrum, and then I don't know if it uses the phase as well.
Yes, it tracks both, changes in both.
Right. And Flux uses a Flux algorithm, and I'm not too sure what that does.
I think it's just an energy flux. So it's a difference in spectral energy overall. So you can think of like RMS of the spectrogram,
right?
In one frame and the next frame. So the difference between that is the flux.
Right. So let's try that. Let's say again with a fretless bass, for example, and see what that outputs. Right. So it's a bit similar, but you can see it will detect some other clicks. Maybe that one. I don't know if that one was there before. But yeah. So this is just another example that we're working on. And I think that's it for the demos for now. So back to Albin. Yeah.
Thanks, Jorge. And as you see, yeah, we are also open to any feedback on the demos. You probably see that we are really good with front end, but yeah, so it made a very simple demo. Feel free to send us any feedback regarding that. Cool. So I just want to mention a few design choices we chose while we trying to wrap up this library. It should be easily installable, like the JavaScript, or like using npm yarn or any package managers, or having some CDN URLs where you can easily integrate into your project. And we want the API as to be simple as possible. It should be modular, as we saw in our native library, and we should be able to customize each algorithm and also allow to build smaller builds of the library with only a few algorithms included. We also want it to be work with the existing web standards, right? With the Webhook API, worklets, and we also rely on the web standards for decoding or reading audio, so we don't implement our own encoders or decoders. And we try to make it lightweight as possible. That means we try to explore the third-party dependencies we have in our native library, like FFmpeg or etc., those kind of stuff. So it's small as possible, and now it's like 2.7 megabytes approximately. And one of the main features, I would say, it's reproducible across different platforms. That is, you can run the same code base in C++, Python, and JavaScript. That mainly important for machine learning applications, because in machine learning world, if you want to do the inference, the model expect the exact feature representation you use for training that model. So imagine a researcher trained a model using Python and using the Essentia features, and you can use the model on the browser using the same feature using Essentia.js. So we had a paper about it today, so you can also check this paper if you're interested about it. And we try to make as much documentation we can within our limitation, and also some examples for you to get started. And just to give you an overview, so these are the level of abstraction. So we have something we call Essentia WebAssembly backend, or Essentia WASM, which is basically the WebAssembly code which cross-compile from a native code. And it can be imported with this JS files in our documentation. You can find links to this. And on top of that, we have a high-level JavaScript API written in TypeScript, which allow you to use this algorithm in a more user-friendly way. So you can also use it in JavaScript or TypeScript projects. And on top of that, we have various add-on modules. That means some extensive use cases like Essentia.js model, which is what we present in this paper today, was about integrating pre-trained machine learning models using TensorFlow.js. So this abstraction allows you to easily use these models in your web project. And then we have something called JS Plot, which is some abstractions to visualize these features on a plot using Plotly.js, and then some custom extractors in this file. So in a sneak peek of the architecture of the library, it's more or less how it is. If there's anything confusing, please ask me. So the main part, if you see my cursor, the main part is this code generator, which is a Python code. Since we have a lot of algorithm and the architecture of Essentia, native library doesn't allow you to automatically map the M script, the C++ to JavaScript. So we need to create a custom wrapper for every algorithm. And this is generated using a Python script automatically. So you can select which algorithm you want. And then once you have that, you cross-compile it to Essentia WebAssembly using mscripten. And on the other hand, you also generate this TypeScript wrapper automatically. And then you can also transpile it to JavaScript code. So combining this, we are able to get a build which is useful to use in browsers and Node.js application, and which has most of the algorithms in the native Essentia. And also mentioning these things, we want to also make a note of some known limitations we have. We figure out, and we are also actively working on resolving it, is that as of now, only 200 algorithms are supported using this JS wrapper we released. That's mostly because the limitation on how mscripten wraps some types. So some types in C++ are not directly mappable to JS. So it's mostly because of that. But you can use all the algorithms if you write a custom C++ wrapper. So that means you can abstract everything. You get an audio input and you do all the things inside your C++ function, and then you can finally return your output to your JavaScript. So we have some example and template if you click the hyperlink, and later Luis is gonna walk us through some examples. And also we have to also point out that we haven't done rigorous quality assessment test on the library. It's still not production ready, and so there's no backward compatibility guaranteed. So we are actively working on a production ready release. You're also most welcome to contribute, because this started last year, and yeah, so we are working on it. So to get started, you can use all these standard ways to import your JavaScript library on the web using npm or yarn, using this command, or you can use in your HTML files just using a script tag, specifying CDN or a local file. You can also import it through the more new ES6 style imports. So if I quickly plot the basic HTML use, you import the library, the HTML, then you load the WebAssembly backend, and then create an instance of Essentia.js API. As you can see, I'm instantiating a class. And the next thing is we want to compute some feature for audio, right? So you get the audio, or fetch the file and decode. In this case, we are using WebAudio API under the hood to fetch and decode. And then once you have the audio data, which is the float to array data, we convert into this vector representation of a vector float to use it in Essentia algorithm. And once you use it, you can manually delete the memory of vectors, since JavaScript doesn't garbage collect the C++ object. So that's more or less like yeah. So the steps to do it in HTML. So if you go to Node.js on left, you can just require the project, and you have all these entry points to various modules. And you can also create an instance to Essentia API like this, similar as in ES6 import. So you can note that here the WebAssembly is loaded synchronously. On the HTML example, we are loading it asynchronously. That's the only difference. So, okay, enough of a lot of talking. I'll try to. So we curated some really hands-on glitch examples. So I hope most of you are familiar with glitch. So it's a kind of a JavaScript platform or playground where you can make your web projects, and you can also interactively edit stuff. So if you click on this link, you can find a lot of different template projects created by Jorge.
Just as a note, sorry, I think I interrupted someone.
Yeah, sure.
No, just as a note, try to, if you can, try to use Chrome or Firefox as a browser, or some Chromium-based browser. But so what I mean is Safari may not work excellent.
Yeah, sorry for that, but I guess most of you are aware as well regarding this. Yeah, thanks, Jorge. So the good thing of glitch, or I think there are also many alternatives, but we found glitch really useful. So if you create a project, you can remix it. So there's a remix your own. That means it create a fork and you can edit the project as well. So let's have a quick at the first example, which is a very non-real-time use case. So you can click this first main UI thread example. So let me know if you can access the project, if everyone can access it. Yeah, all good. Okay, so we will come to this project. So you can remix it if you want to edit it. Otherwise, you can just click this button. So if I click view source, it will load this window. On the left, we have the code, and the right, it just render the HTML the web app. So if you click on top, there is something called show. If you don't see the web app, you can also click next to the code, so you can see your web app rendered on the same window. So on the leftmost side, you can see different files. So you have a README, you have an index.js file, HTML file. It's pretty basic. You have the headers, the things concern us. We are importing Essentia.js here. You can see on the script tag, and also this main.js file, which I will show you after this. And we just have some DOM elements, USF buttons, and things. And we are also loading an audio file here. We're not loading just to visualize on the DOM. So if you click on main.js, it's where most of our JavaScript file stays. And on top, we're just creating an instance of every API, audio context, and then some global variables, selecting some DOM stuffs. Yeah, so I will come back to these functions after. So first, let's go to this callback window on .load. So basically, once your HTML DOM elements are loaded, all this chain of functions go and execute. So you just specify once everything is loaded, do this. So once everything is loaded, we create Essential Awesome. So instantiate WebAssembly code. Once it's done, we create instance of Essentia, and we are also just attaching some events to a button. So for example, when I click this button, analyze, I'm getting this output, right? RMS value of this audio signal. Right. So I'm attaching some events to this click. So basically what I'm doing, I'm fetch the audio and decode from the URL. So we have a URL to the audio file. Once we decode the audio, we send the decoded audio to this function called analyze, which we can check, which if you go up, you can see a function called analyze. It's get the audio data in float32 array, and we are converting into vector float, and then we are passing into this RMS algorithm. So you can basically use any Essentia.js support algorithm here, this function, or connect it together to compute some feature. Once you're done, you just delete the vector, and then you output the features. Like in this case, it will be a JavaScript object with the key and value. Once we have, I have a function here to just display the result on the top. So it's simple as that. Let me know if anyone is confused with this basic example. So otherwise, we can go through, because this is not an ideal, it's fine with RMS, but ideally we should not do all audio processing or audio analysis on the main thread. It's now everything is happening on the UI thread. But if you're building more UI heavy steps, it makes sense to move everything to a worker. All the stuff related to audio processing can be in a worker, so it doesn't block the UI. But it also depends on the algorithm you're using, so because RMS is something doesn't block your UI thread much. So, but some algorithms are computation heavy, so you might need to put it in a different thread. Okay, so if you don't have any doubts, then we can go through the example of workers. Oh, no, sorry, workers. We are gonna go through an hands-on with Jorge, where he's gonna help us build some stuff.
Yeah, let's have a go at that. So I'll share my screen now. Yeah, so like Albin said, it's not ideal to do our stuff in the UI thread as soon as you start building more complicated applications visually. So, so can you see my screen? I assume you do.
Yes.
Thanks. Right, so if you want to follow along, we'll have a brief look at the workers example, which is a slightly more appropriate way of using Essentia. Sorry, I shouldn't have done that. Yeah, so just go to glitch if you want to be like touching the code. Just again, don't forget to remix the example, the template. But yeah, the code will look very, very similar to what you just saw with Albin. The main difference is that now in main.js, you won't have an analyze function, right? So earlier we had an analyze function here where we were doing our Essentia analysis. Sorry, sure. Right, but now we have our Essentia analysis happening in the audio worker.js file. So it will be here where we import Essentia and its WASM backend, okay? Because we're using workers, and so this is, by the way, so we're doing this because this will happen in a separate thread, but I'm assuming most people here are at least familiar, vaguely familiar with workers. So we have to use a slightly different build of the WASM backend. So we're using this UMD build of the Essentia WASM backend because we're using import scripts and, yeah, like dependency, like importing dependencies in web is a bit of a mess. So we do that. We instantiate Essentia with its WASM backend. We had to add this little, again, related to the mess of importing libraries in web. We had to add this little exports object so that this UMD could work. We're working on fixing that. So we instantiate Essentia, and then we have our analyze function from earlier. It's exactly the same function, but we have it in this worker, and we're using it whenever we get a message from the main thread, right? So on message, we will grab the audio that we're passed from the main thread and give it to our analyze function, and then send it back on post message. Simple as that, but that already kind of offloads. So by the way, this works the same as the other example did. But it kind of offloads that computation to a separate thread, and we will notice that as soon as we are doing any other pipeline that's a bit more complicated. So just to get an idea, how many people here work with Node or interested in backend? I saw. Okay, I saw. Sorry, what's your names are? So I saw. I thought I would see the names. Why can't I see the names? So I only see Danny. So I know Danny. I've seen Danny raise a hand. But maybe you guys.
Hans, Mateo.
Antonio.
Right. Okay. Thanks. Because I can't see the chat. I can't see the chat. So also, if you're writing on the chat, I cannot see that.
Not particularly interested in the server side, but I use the Node.
Okay, well, just for brevity, so I'll let you know. So going back to the slides, the next example is Node example. It's very similar, but the import is synchronous, right? So going back to what Albin was saying, it's more of like an ES6 type of import. But because it's a bit more involved, because it's, it has a server side, but also a front side. The template is there, so please feel free to go there and check it. On this, like on the surface, it looks very similar to, so it doesn't work. Let's see. Okay, so what I will do is revise it and then get back to you. But this should be a template to use Essentia with Node. This is complaining about some sort of
No worries, we will manage to fix it.
Yeah, well, so anyway, that template is there. I will fix it and let you know on the Slack what was wrong and when it's fixed, but it's there. So next, I'm going a bit fast because I want to move on to the real-time stuff. This will let me get back to the presentation. Okay, so back to the same slide. The next examples, so if you want to start going to glitch with the script processor node example, which is the first way to use Essentia in real time. So going to glitch. Again, remember, feel free to remix this. So you will need a glitch account, but it's super easy to create one in order to be able to interact with the code, but it's nice. And this is using the, as many of you here will know, it's a deprecated interface, script processor node, but it's a super simple way if you're prototyping and just want to get started with making stuff real time, and in this case, trying some processing pipelines with Essentia. This would be a super easy way to work with real-time audio. So again, I'm going to start at the bottom with the window load. We get our audio context and instantiate the Essentia, but using the asynchronous WASM import. And once that's done, we're listening on the button. When we click on it, we'll start, and so start will request mic access. Okay, so that's this little thing here using media devices, and that will give us the stream. The mic stream in this start audio process function. So we will, there's a bunch of checks here to ensure that the mic stream is active and the audio context hasn't been stopped. And then we create the necessary audio nodes, right? So we create a media stream source node for the mic, and then we have our own custom node to use Essentia in. So that's the script processor node. So we're using it with a size of 512. Samples, so we have to use the on audio process event, so that will make sure that our custom code, which is this Essentia processor function here, gets called every time there is new audio. So that's this little function over here, which in essence looks similar to what we were doing earlier, but instead of loading a full audio track, what we're doing is on audio processing event, it's basically telling us there's a new frame available for you to process. We get its input buffer and also the output buffer, although the output buffer we're not really using. So we get an input buffer, get the channel data, and then we are converting that to vectors because that's the type that we use for Essentia.js as input to most algorithms. And we compute the kind of default example of RMS, and we will, we'll display in that. So by the way, this is, if I speak loudly, it should reflect there. And so that's the most basic real-time example we could have. Important to clean up. So these vector objects, they're not cleaned up automatically by JavaScript. So we should make sure that we call the delete method. All right, so this is the most basic way to get started. So now if I'm gonna ask you to actually remix the next, actually remix this example. and I will do it with you, and we will try to implement core detection that we saw at the beginning with Dmitry. So Dmitry showed us a basic pipeline. If you remember in the slides, we had this sort of pipeline up where?
Bit up.
Up here, sorry, yeah. So exactly, so we're going to try and implement this and see if we can detect some chords in real time. Okay, so again, I'm going to ask you to, sorry, this is not the example. So I'm going to ask you to remix this. I'll remix it myself. So if you come up here, you see this button again, remix project. So I'll make a copy of it, and Glitch gives it funny names like this. But yeah, so we'll make some modifications to the code so we can do chord detection. So the main thing we will be modifying, obviously, is the our custom processing function, Essentia processor. So if you want to come down to that function, then what we will do to start with, and just to make sure, is everyone, I mean, everyone that's interested, have you been able to remix the project, and is it working on your computers? Like all of that, is everything looking good?
Yes.
Nice. Right, so the first thing we're going to do is get rid of RMS. We are not interested in computing RMS anymore. But actually, we will leave the audio vector delete, because as I said, that's important to clean up our memory, and we are going to be using audio vector as our input. So that's every kind of audio frame that we're getting on the audio processing event, right? So from there, the first thing we will have to add, and just to be super transparent, I'm copying code definitely, but I will be typing it out. So we're going at the more or less the same speed. I'm sure there's faster typers than me in this call. So the first thing will be to window the audio. Okay, so we don't need. We're kind of skipping the frame cutter, right? So frame cutter, we've already got that from the script processor node, right? So we're working with each frame of data. So the first step next is to window the audio. So we'll call this our windowing output, right? This is what we will get out. And so we'll use the Essentia windowing algorithm. Okay. And so it takes a few parameters. So it takes the audio vector is our first. So that's the frame. And please let me know if you run into any problems or anything, or if you want to ask whatever. And then every algorithm will have a bunch of parameters that frankly, I don't know by memory. So we can go to the documentation in Essentia and have a look. So windowing, the next parameter is normalized. So by default, we're going to say that our input, we should normalize the window. And also we should give it a buffer size. So buffer size, I think, is a global variable we set somewhere. No, so we need to set it. Okay, so let's set our buffer size. Okay, variable, and let's use something big because we're computing chords. So we should be able to look at a fairly big chunk of audio. So let's say 8,192. So multiples of 2 tend to work well. Now make sure to use that same size in your script processor node. So instead of 512, let's use buffer size. Okay. And so we're using that as our windowing size. And next is the type of window we want to compute. So in my case, we're using a Blackman-Harris. So Blackman-Harris 62 is a specific type of Blackman-Harris. And so that's our windowing done. Next up, if we go back to the pipeline, we need the spectrum. So again, we'll come back to our remix project. And so this will be, this will be the spectrum output. So again, Essentia spectrum algorithm, and we'll use the window out. So then most Essentia algorithms will output an object with the, because some of them output several values, right? Maybe it will output the pitch and also the confidence. So it will be an object and then inside the properties. So in this case, frame, window out frame. And again, we use the same buffer size as the size of the FFT. And next in the pipeline is peaks, right? So spectral peaks. We want to find out what are the most prominent frequencies in the spectrum. Keep going back to the documentation instead of the. So peaks out will be where we get our peaks. So Essentia spectral peaks will compute the peaks for us. And as an input, we will be using here spectrum out, obviously. And again, so this outputs an object, so we grab its spectrum property. And then again, back to the documentation, we will have a bunch of spectral peaks. Will give us what parameters we need to use. So after we've given it the spectrum, it wants magnitude threshold. So we're just giving it 0 for that. The next, I guess, is the maximum frequency that it should detect exactly. So that's in hertz. We're using 4,000, for example. I think the default is 5,000. You can try and see. The next will be the lowest frequency to detect. So that's we're going to go with 100 hertz. Sorry, no, that was a maximum number of peaks. So that's 100 peaks. And then minimum frequency is 0, and we're using 60. So kind of a typical use of a low-pass filter to get rid of the rumble. Next, so we say order by, so order by frequency. So I guess that will order the peaks by frequency. And the last parameter. So this is one example of something that we want to improve in our interface. And if someone has any idea, so okay, so this is the audio context, right? So we need to grab the sample rate from the audio context. So one thing that we need to improve is having to give all these parameters, especially when you want to only give the last one. So let's say that the sample rate was the only variable thing in my application. The way that Essentia is designed right now, we have to kind of give all the previous parameters to be able to get to sample rate. You cannot just give it sample rate and have the rest be the default, right? So that's one thing that we still have to improve in the interface.
Yeah, just to add to Jorge, so it's basically because we did a one-to-one mapping to the like Python binding or a C++ binding. So in Python, you can do that. Like you don't need to preserve the order. In JavaScript, you have. So we are working on making the parameters pass as a JavaScript object. So you don't need to care about the order. So this will be changed in future, but for the moment, we have this order. Yeah.
Yep. Okay, so the next step, before we get to computing the class profile, there's one optional step, and that is to calculate whitening, spectral whitening. So that might improve detection of HPCP later. I don't fully understand what this does at a signal processing level. Maybe Dmitry or Pablo or Albin can chip in, but we're using this algorithm from Essentia next. So we're getting our, let's say, whitening out. We're going to call this. And again, using Essentia, spectral whitening. And we use the peaks output to use, sorry, no, my bad. So for these, we're using the spectrum output again. So what we have up here, spectrum out. Okay. But we will use the peaks that we just computed as some other parameters to the widening algorithm. So peaks out, and we will use frequencies. So peaks gives us where it found the peaks and also what magnitudes it found them at. I'm guessing that's some sort of maximum frequency parameters. So yeah, max frequency. We're setting it again to 4,000 hertz. And again, we need the sample rate for this. So we grab the sample rate from the audio context. Okay. And we're almost reaching the end. So the next step is to compute the pitch class profile. So that would be essentially what nodes amongst the 12 nodes in the 12-node equal tempered system it can find. So that's this step here, right? HPCP. You could compute many other pitch class profiles, but this happens to be just one of them. So let's go and look for HPCP in the documentation. So this has a bunch of parameters, and maybe I won't bore you with all of them and just copy them. Okay, so we'll use again Essentia. This is all in caps, HPCP. And so we need to give it the peaks output. So it needs to know where it found the frequencies. And then we will give it the whitened magnitudes. Okay, so whitening out and use its magnitudes output. And the rest, again, I'm just going to copy because then it will be faster and less boring for everyone, hopefully. So just bear with me. And is everyone following all right? And like, does it make sense?
Yes, to me.
So we will do a bit of a short test once we've got this to make sure that we do have some note detection. So again, here audio context and sample rate. And the last one is 12. So that's probably, we want 12 notes detected. So right here, let's, so I'm guessing you have something very similar to what I have here. We just modified the Essentia processor function. And remember, we added a buffer size here to be quite big, so we can easily detect like tones, right? So more kind of temporal stuff, sorry, frequency stuff. So the next thing is to, first we're going to check, before we get to the chord detection, check that this is working. So this is a simple function that will display the results on the DOM. So HPCP, let's just have a look at this. So HPCP out, and let's see what we're getting here. So yeah, if I run this, let me see just what we're getting. So we're getting nothing.
Jorge, in line 83,
yeah,
you put as input window out instead of windowing out.
Aha, okay, thanks. Is that what this is complaining about? Yeah, window out is not defined. Thanks. Yeah, things about live. So line here, yes.
And I think perhaps you need to convert the HPCP array.
Right, right, yeah. So this we will have to do HPCP array, just because vectors is what Essentia works with. So we will do vector to array, so we can print it out and see the numbers. HPCP out. Is that right, Albin? Or does it? Oh yeah. No, I need to grab the HPCP from the object.
Yes.
That's the only thing. HPCP. That's it. Okay, so that's what it looks in the end. HPCP array. Hopefully I haven't messed up any names now, and it will run. Nice. So now it's detecting how strongly each of the 12 notes is present. And well, in my speech, none of them is too clear, I suppose. But at least that step is working. Is it working for you guys? So far, so good.
So note that here 0 is A and 11 is G sharp. It's a tone from A to G sharp.
Right. Okay, so shall we continue, or are there any? Cool. Okay, let's stop this. It's going crazy here. So yeah, the last step missing, which in fact I don't think is present in. Yeah, so Dmitry's example is his computing key. We're going to feed this HPCP to a chord detector, right? So in Essentia, back to the documentation, we have a chord detector algorithm, I think. Chord, oh, maybe it's chord detection, sorry. Yeah, chord detection. No, chord detector.
I think there are 2 or 3 functions similar.
Okay.
Descriptors and detectors.
Yeah, I'll just look it by. Right, so it's chord detection. I don't know why it doesn't find it. Chords, it's chords detection. Yeah, that's why. So it needs some sort of pitch class representation. We have our harmonic pitch class profile, HPCP. So let's do that. Now, as you can see from documentation, this algorithm takes vector float. So another one of these quirky data types that's not JavaScript. So going back to the example, let's get rid of this array conversion here. So right after the HPCP, we will first of all create a special kind of data structure that we need to store our HPCP. So that's we're going to call it HPCP pool. Okay, and we'll create it using Essentia module vector float, okay, which is the type that core detection takes in. And then for every frame that we get in this function, we will do HPCP pool dot pushback, and that will add it to our pool. So we'll take the HPCP object that we have up here, and its HPCP property of the object, HPCP out, yeah. And now we're ready to use the core detection algorithm. So we'll go core detection out. That's going to be my variable. So we use Essentia chords in plural quotes detection, and we're using HPCP pool. So this is our vector float type. So we're good. It will hopefully understand. It also needs to know our buffer size, which is this global we declared earlier, and the audio context sample rate. So maybe should shrink this. Cool. So that's our core detection. Now this will output a couple of things. It will give us chords. Okay, so if we chord detection out, this will give us chords, and it will be because it could take multiple HPCP inputs. So we're gonna grab the first chord that it detects, and also gives us chord strength. Okay, so chord strength. We'll grab chord detection out and get its strength property, and also get the first one, because as I say, this is happening an array. And again, typical cleanup. And yeah, and let's output this and display this to the DOM, and see what we get. Chords. Okay, so that should work. Are you guys following and not too much typing? Cool. So yeah, let's hit start and see what this does. Okay, so it's throwing a bunch of garbage. Let's get it back our trusty melodica. So this should be an F major. Okay, and this should be minor. Okay, cool.
You can also print the strength, Jorge.
Yeah. So one thing we could, the strength would be useful to do something like this. For example, we could say we could have like a little gate that will say, if chord strength is greater than. So this is like a nominal, like a 0 to 1 value. So let's say if it's stronger than 0.7. Right. So if you're pretty confident, then display the results, right? So we'll have this here, and that way we don't get so much false positives, right? So let's try this again. So it's not displaying anything now. Oh, now it thinks it heard a. Okay. A different chord. B flat. And one thing that's interesting, so this will only detect, so it's a simple detector, so it will detect major or minor. For those of you that know some music, I don't know if everyone here knows about like music stuff. But it's something that's interesting. For example, if you have like a minor 7th chord, right? That's essentially like a mixture between a minor and a major. You could, like, for example, D minor 7th could be like D minor and F major. So this won't be able to detect the 7th chord, but you will see it oscillate between the two. So like you can see here, like this would be D minor, right? And this would be F major. That would be D minor 7. So what we'll see here is that it detects kind of both and it oscillates. You'll see. Right, so it kind of oscillates between F and D minor because it doesn't really know what it is, right? So yeah, that's our basic example. Have any of you tried it, and is it working? And did I? Yeah.
Jorge, can I ask a question?
Sure.
So is it possible to get the pitches out so we can actually see which note is the bass note, and then we can do our own chord logics to estimate like a 7th chord or a 13 or whatever, you know?
Yeah, so you could go back to what we had earlier with the HPCP output. So that, if you remember, gave us.
So we get the different octaves, and we can analyze where's the bass note and where's the tension.
I'm not sure if you get the different octaves, so I don't know if the HPCP algorithm.
So the HPCP basically give everything in 1 octave. So all the notes are put to 1. So you can have the bin size there, it's 12. You can also say the double the size, 34 or 64. So according to the size of the bins, you compress all the notes to that much octaves. So by default, it's 1 octave. You can also increase it.
So does that mean
possibly the bass note would have like a higher rate on the scale between 0 and 1 though, because it's like louder, I guess, or more emphasized or so.
And also you can also configure it in the peaks and the HPCP algorithm, the frequency range you want to detect the chords. Yeah. So there are a lot of parameters there you can change, which have a drastic effect on that.
So Albin, so does this parameter, the 12 bin here, does it mean that if I set it to 24, it will detect 2 octaves? Is that what it means?
Yeah, I think that's what I understand.
No, that's not it. All the octaves are summarized across. Well, we summarize everything across all the octaves, so you just have minimum and maximum frequency. So what you could do, you could probably run a lower range of frequencies that you want to compute the HPCP on, and so you could have one range for bass, and then a separate range for, well, a more general range or for higher registers.
Right.
We also have some algorithms that you could summarize spectrograms into basic scent spectrogram. So you would have, you define the resolution of each bin in cents, and you could just map the entire spectrogram to a basic kind of tonally scaled spectrogram.
You could also look for the lowest peak probably, and
as well.
It's not going to be the best way to find the lowest note, but it's been used before.
Right.
I have another question related to source detection, and well, it's a little bit more general, because from what I understood, the HPCP pool is just an array of nodes or pitch classes or whatever, or an array representing pitch classes. So it's not audio, what I mean.
No,
so
it's not audio. No.
It takes that, and then why it needs the buffer side and the sample rate. And
which
maybe if it's using audio, I don't know.
You mean the chord detection algorithm?
Yes.
Right.
My question specifically is that algorithm acting on audio or from the previous pitch class extracted analysis results?
No, actually, what we did here, we reused an algorithm called chords detection that, in fact, is working on the kind of matrix of these HPCPs stacked together for the entire song. So what this algorithm will do is output multiple values. If you remember, we took the first value.
Yeah, that's why you use a vector.
It cuts out into segments of 3 seconds and tries to estimate on each 3 seconds by default the chord. So it's a very naive kind of chord estimator that tries through the entire track. It will output you a sequence of chords.
Right, so it's made to work on multiple frames, right?
Yeah,
that's why.
And we just reused it on a single frame because we can.
Right.
Which is probably not very, let's say, obvious. I mean, we could, in the same way, use key estimation algorithm instead of this chords detection. But yeah, basically, we don't have an algorithm right now that would just work with a single frame. Because typically we accumulate a bunch of HPCP frames together. For example, you would like to estimate chords on, for example, segments of the song between different beats, which probably makes sense. So you can identify the onsets or beat positions and try to estimate chords on the between.
I see.
Exactly.
And also regarding the question about the sample rate, I think it's because the algorithm needs to know how to map peaks to the frequencies. So if the algorithm works in a different sample rate, this is the way you do this mapping internally.
Right. Yeah. So that's why you need the sample rate. But assuming that you know that we were working with the default sample rate, which is I don't know what it is. Yeah. So 44.1. You know, maybe you wouldn't need to pass in the buffer size in this particular case, because we're, as Dmitry said, we're using this algorithm which is meant to work on multiple frames, right? So you can imagine if instead of real time we actually use a frame cutter, right, on a full audio file, and we compute HPCP for each frame of that audio file that we've cut it in, then this variable here, the HPCP pool, which is a vector float, it would be an array of HPCP arrays, right? And each would correspond to one of those frames. And so in that case, it makes sense, right? The core detection would have to know what the buffer size is, so we can kind of average over each three, I think was what Dmitry said. So yeah, it kind of doesn't make a lot of sense in this use case, but that's why it needs it.
Actually, just as a comment, any feature requests to the upstream Essentia are very welcome. I mean, some things we sometimes discover that they're not the optimal. So then we change. So if some users need something, let us know so that it's at least registered. And when we keep this in our mind.
Okay, well, we will have a very short, a Q&A session just in a few minutes. So let me just quickly finish and show you one more thing. But yeah, like make any questions if you want, or write them down, and we can talk about that in a minute, right? Keep it open if you want your own kind of fork of this template. So going back to the presentation, there's one more thing that I want to touch on before we go on a break. So briefly in these 5 minutes that we have, sorry, that's the next section. Yeah, so this is like the most basic real-time use, as we explained, with deprecated script processor node. But many of you here, I'm sure, know about audio worklets. So that's kind of what came after a script processor node, and it runs custom audio processing on its own audio rendering thread. So let's go have a look at that template, which again is like the most simple example I could think of using Essentia with audio worklets. We use audio worklets with many of our real-time demos. Again, if you want to interact with the code, remix the project. So in this case, we have a few more files. So not everything is happening in the main JS file. But a lot of it is very, very similar. So we still need to request, the user for access to the microphone. We still, when we get the microphone, we will create a few, so ensure that the audio is on, and create a few audio nodes. And in this case, I'm using analyzer node to get our output back, but no need to get into that. So yeah, so the main thing is we creating audio processor. In this case, it's this asynchronous function up here, which will get our URL to a custom JS file. So that's the Essentia processor JS file up in the scripts folder. And exactly, and so we use audio worklets to add the module. So that will kind of add our custom code to the audio worklets global scope. And we create the audio worklet node with our custom name. So I've called it Essentia processor because you can't have Essentia in too many places. So the main code now is in Essentia processor.js. And if any of you have used worklets before, this will look very, very familiar and very simple. Here we have an ES6 kind of example of imports. So we're using ES build of Essentia WASM backend. We import that, and this is a simple class extending the audio worklet processor class. So we'll just create an instance of Essentia, and we'll create a kind of a variable for our descriptor value. In this case, we're going back to the RMS example, and every audio worklet needs a process function, which will give us 128 samples. This is fixed until the specs change, at least. And so this will have its own set of challenges for real-time analysis when we want to do more complex spectral analysis, like we just did with the chord detection. If anyone has any doubts about that or interest in that, let us know later. But for now, we're just working with those 128 samples. So input lists could have many possible inputs. That gets us the first input. This is then itself a list of channels. So each input could be multi-channel. So we're grabbing the first channel. So this is a very simple, assuming mono audio case. And again, we convert to vector, Essentia RMS of that vector, and we send to the output. Super, super simple. Clean up the vector when we're done, and return true to keep the audio process going. That's it. But already this means that our custom processing is not happening in the main thread. So it's happening in its own audio rendering thread. And so everything's a bit more streamlined. But yeah, so I think with that, we reach the end of the first half. So any questions about any of this, please go for it.
Okay, maybe you want to also show that ring buff thing, like quickly go through.
Yes, I mean, I don't know if people want to see the ring buffer example.
Yeah, just to add a comment, it's just if you want more than 128 samples for doing your processing, you can have your own data structure, usually a circular buffer to accumulate and do the processing inside the class. So yeah.
Exactly. Yeah. So in this case, if instead of using Essentia processor, we were using this other JS file in scripts folder, ring buff Essentia processor. This looks similar, but we're using, so this is a Chrome Labs utility kind of code that gives us a kind of a first in, first out type of structure, ring buffer. And that will basically make it super easy for us to accumulate frames on the input. And also kind of recreate the concept of overlapping frames. So in audio processing in general, and MIR in particular, sometimes, especially for spectral-based processing, you want to have some sort of overlap between consecutive frames. So this is also the way to do that. And so for that reason, we want to have, so generally you have a size for the frame, and then also a size for the hop size, so how much of an overlap there is. And that usually will be some sort of integer ratio of the frame size. So if your frame size is 512, then maybe the hop size will be half. So we'll have half of overlap. And for that reason, we need kind of two separate FIFO, the separate ring buffer structures, right? One with the frame size size and another one with the hop size, right? So that's what you see here. That's kind of extra. And new is creating this ring buffer with hop size and a ring buffer with a frame size. And then these are two kind of arrays that we need for these structures to kind of pour their data in and out, right? So that's like a container for the ring buffers. And it's of float32 type, but it's an array of float32 because you can give this ring buffer multiple channels. So that's why it's an array of float32 arrays. So the rest is relatively simple. Here I kind of added a way to kind of switch on, overlap on or off from the main thread. So you could send it some sort of message. So if you go back to main.js, you could see you can send an options object to the processor, and you can set your frame size, your hop size, and you could set overlap to true or false if you don't want any overlap. Generally, we want some overlap in MIR. And so then the meat of it is whenever we get 128 samples, that's the default in audio worklets, we will push that into the ring buffer of hop size. And then if we have some, enough frames available, then we will put that into the frame ring buffer, right? So that will be generally bigger than hop size. And that's it. So we will always be pushing the previous samples that we had to create that kind of overlap hop size. So we always push the previous data in hop data, and then we will get the new hop data that's available in the ring buffer, and put it into frame ring buffer, right? So we create some sort of overlap. And yeah, and then whenever we actually get enough data of the size of our frame size, so again, for example, it could be 512. So we check that like this, frames available. And again, this will vary depending on the ring buffer implementation that you use. So for example, I know that Paul Adenot, who I think is on this conference and is one of the main guys implementing web audio in Firefox, he has a different implementation of a ring buffer. So, you know, this interfaces will vary. But if we have like in this case, for example, if we have 512 samples, then we will actually use Essentia, right? So we're using the same algorithm than before, but we're computing it on a bigger frame, right? Yeah, that's as quick as I could do it.
So machine learning on the web is the new thing. As we saw in the past few years, so there's advancements, and of course for us the big one is TensorFlow.js, because it meant that we could use the models, the deep learning models that because we work with TensorFlow, we could now port them for TensorFlow.js. But there are also other initiatives. There's talk about having an open standard format as well, probably in the future for the models. The Magenta did some applications that include deep learning on the web. Albin, anything to mention here?
So yeah, I think Magenta is still using TensorFlow.js. And actually Magenta and things like ML5, they basically try to make abstractions on top of models that enable wide range of developers to use these technologies, right? Because we're going to mention that these machine learning models are sometimes require some domain knowledge to use it. So, and most of the developers probably don't want to know that, or to facilitate creative application or even some other industrial application. So we can also see there's a trend of abstraction libraries which allows people to use machine learning models. So for example, like Magenta and ML5. And then there is also framework like ONNX, which is a framework of serializing models in a specific format, which allow you to do inference on a server or also in JavaScript, actually. But somehow we found that was not suiting for our use case. So yeah, I think that's it.
Yes. Meanwhile, we were working on TensorFlow models within Essentia itself. So we realized that in many applications nowadays, of course, the intrinsic part is machine learning in music information retrieval, at least, that we covered before. And Essentia is basically a collection of algorithms that you can use to compute many handcrafted features. And we thought that we want to expand it towards this direction. And of course, also one of the reasons is that we already have algorithms to compute typical input representations that the model need, spectrum representations, such as, for example, Nell spectrograms. Just for a reference, using Essentia, you can have significantly faster computations on a very large scale if you're analyzing collections with millions of tracks that we do on our servers. We find that it's very useful to have an extractor written in C++, optimized for computing these input spectrograms that we could pass then later on to TensorFlow. So in that sense, we continued working on building models on top, and we have algorithms for different input representations that are typically used, and we can actually, so as you can see here, typical model is working by taking audio, computing Nell spectrogram or any other representation, maybe constant Q, and then from there there is a model. No, and often the bottleneck for portability is that people would use for training their models different types of MEL spectrograms. Maybe you know that there are different parameterizations that you can use there, and basically to reuse someone else's model without using their code, without dependency on their particular code, you have to recreate the MEL spectrograms exactly like they are computed in their code. And Essentia allows to parameterize pretty well the steps necessary for that. And we reproduced a few commonly used MEL spectrograms that we found in literature, well, in available models, pre-trained. But basically, after getting this input representation, it's passed to the model, to our models that we have pre-trained, and these models can then retrieve different semantic concepts such as music tags, genres, styles, moods, danceability, instrumentation to a certain extent, presence or absence of vocals, gender of vocals. We also added a model for tempo that we took from our collaborator. So the interesting thing is that we can now take some new existing models that researchers create, and we can see if we can recreate the input that these models required, and we can just port them to Essentia. And what it also allowed is to run those models in the applications that are decoupled from this typical research pipeline, which is just Python, right? So you could take this, and if you compile these, you probably can run it cross-platform, including mobile platforms or some different devices that we probably can be limited otherwise. And you're welcome to visit our link explaining our models here. But this is an example of how tagging and classification works. So this is a song that we all know, Queen, Bohemian Rhapsody. Interestingly, it's exactly six minutes. At least this version that we took of the file to analyze. And it's all here at your view. And what we do is we compute this input representation, MEL log spectrogram. You can see it here. And now in Essentia, what you can do is you can go through different segments of this song, and each of these chunks, which is a few seconds long, up to 3 seconds long in the current models we provide, so which is the receptive field of the model, is the segment of this spectrogram that we will pass to the model. The model was pre-trained on this type of inputs, and it will generate predictions that are a little bit smeared here, but you probably can see. So there are some classes. So these are a few classifiers that are running predictions on this chunk, and they can say if the music is, for example, classic, or if it's folk country, or if it is ambient, if it's instrumental, does it has speech, and stuff like that. So is it sad or happy? And on the global scale for the entire song, it will look something like this. So you see here this is the same 6 minutes, and this is the evolution through Queen, Bohemian Rhapsody. This song has a lot of variation, right? So this is 2 auto-tagging models on the left, and on the right, it's a bunch of classifiers that we also trained using transfer learning approach. So starting from the auto-tagging models, we actually reuse their feature embeddings in internal, not the predictions, but the layer before that, and we use that as an input to the second classifier, which is a very lightweight, and it's able to classify into genre, into moods, and so on. There is, I'm not sure if we could show this, if that makes sense. Well, I cannot show it because I don't have audio set up, but you will see here, if you click here, you will see there's a few videos how this runs online in a Python notebook. Going back to web, well, we have, for Essentia.js, we provide a few models. We could not provide all of them. I mean, there are scripts that we can use to convert, but some models are still in work in progress. So for now, we share these ones. So we have a few for auto-tagging. You can see they vary in complexity. We have one model from trained by Google that is VGG, is trained on audio set. It's for acoustic event recognition and sound classification. And this model is super huge. It's trained, it has 62 million of parameters, and it weighs a lot. So it weighs, as you can see, over 200 megabytes. So we provide it, but we are not sure you will be able, I mean, we don't know if that's useful for web audio. I mean, that's very weight heavy models, but the models that we think are useful in our demos are of size of 2 to 3 megabytes. Yeah, you can follow our publication to learn more about the models. I think not for the sake of this tutorial, that's fine for now. And as I said, some of the models we have are classifiers that are reusing some other models that are kind of source models that generate some embeddings that are then. So the idea of transfer learning is that we can train on a very large data set, which we have, which is somewhat related to our tasks that we want to work with. So on this very large data set, we can create a model and we can this model will learn some features. So they will be automatically learned. And those features then we hope they will be useful for target tasks. And target tasks on the right. This is a table of classifiers we have right now. As you see, we have one actually for sounds like air conditioner versus car horn, children playing. So, well, just some research data sets that we used to train these classifiers. Yes, and now you can see all the models are available at this URL, and there's description. All the models are under Creative Commons license, non-commercial, non-derivative. And here you can see the repository where you can go by task. So if I want to work on classifiers, I can click here. And I can go to, I want to work on, I want to know if the music is happy or not. So I go to mood happy, and here are all the models. And among those, you can see TF.js. So these are the models I mean, the originals and then the converted TF.js versions. And actually that's it for, so now Albin will explain how this works inside Essentia.js.
Yeah, thanks, Dmitry. So, yeah, so as Dmitry mentioned, all the models are available in this URL, and you can also find metadata of this model, like the data set and the classes, accuracy, etc. There's also a JSON file inside those directories you can check. So a natural choice for integrating into the web was to use Essentia.js for feature extraction and import these more converted models to TensorFlow.js. So a typical pipeline would be like this. So you have on my left side, my cursor. So you have an audio input, which then we do some pre-processing, usually like downsampling the audio or smoothing, etc., required for the feature extraction. And then we do the feature extraction. In this case, we want to use Essentia.js, and then it is fed to the model for inference, and we can use TensorFlow.js to do that. And it outputs some results, and we have to do some sort of post-processing, and then you get the prediction. So this is like an end-to-end pipeline of using this sort of ML models for audio analysis. But often, you know, these two blocks of feature extraction and inference often need some sort of domain knowledge. Like you have to be familiar with the ML audio or generate overview of things to need to connect and customize steps. And this can be a pain in the ass for people outside the domain, right? So we want this to be accessible to everyone in the wide spectrum of web community to able to use this technology, right? So we also integrated an add-on module to the library called Essentia.js model, which is basically a JavaScript abstraction on top of this existing libraries we mentioned. So with the new pipeline, it will be like you have an audio input, and then you get the prediction. So all the intermediate processes are abstracted away with this JavaScript API. And you can also, it's decoupled, so you can also send feature extraction to a worker and inference to another worker, etc. You can check more about in a paper we presented on Web Audio Conference this year, and also the documentation for more details. I'm gonna walk you through kind of a gist of the API on the next slides. But before that, let's see how these things work, right? So before we get into code
see how these things work. I'll share my screen and show.
Thanks. Okay.
Very quickly. Some of you will have seen some of these examples. Oh, sorry, I need to share with audio. And in fact, the first thing I'm going to do, if you will excuse me, is to check that you can hear audio from my computer. So I'll play just some. Can you hear anything? Yeah?
Yeah.
Okay. And is it loud?
It's loud.
It's a little bit loud. Okay.
Maybe a little bit less.
Okay, so yeah, let's try with the
ear.
Is that a bit less? Is it okay?
Maybe a bit more or less.
A bit more or less. Yeah, I think this fader from YouTube is a bit, yeah. Too quiet now, maybe? Perfect. No? Okay, that's perfect. Okay, cool. So yeah, let's go with that and hope that it works. The reason I have to do this test is because I'm going to be feeding the audio directly, so without any microphones in between, so directly to the demo. So I'm going to be showing first this real-time auto tagging, which many of you will have seen, or some of you may have seen in our paper booth. We showed this briefly a couple of times. So let me check that I'm actually grabbing, audio from where I want to grab it. And then I'll go back to this heavy stuff and do some. Yeah, no. So you can still hear the audio, right?
Yes.
Yeah, I don't think this is getting the audio. So let me just check very quickly. Right, no, it isn't. Let's try now. Can you still hear the audio?
No.
No, you can't hear it now.
No.
Right. So, yeah. I don't know how to do this. Because I think Zoom is taking the audio from into its own device and it's messing with my setup. So maybe I'll have to do the microphone thing.
Yeah, sure.
Or you can just trust me and know that this is rock. Even if you don't hear it. No, that's not cool.
We trust you.
We can also run the video that we got to Twitter now.
Yeah,
which
sure.
Is essentially the same. So I ran it yesterday through the same setup that he's trying to rerun now. So we can maybe just.
I can say that I've seen it in action yesterday.
Maybe
I also added a video today.
Actually, by the way, yesterday I was playing with this and I was running this system live while we had performances. We have very good performances, and so I captured the audio, and it was saying that the music yesterday was between ambient and experimental and electronic. So it really captured for that particular case very well.
Can you hear any audio?
No.
No? Okay, I'll go back to what we had earlier, which was, whoops, this Zoom audio device. So now you should hear some audio. Whoops. Quality is a bit bad. How do we make the quality better?
If you start playing, it will normalize.
Okay.
Beautiful, it feels so right to see you lying in my bed under this pale red light.
get it. Let's get lost now, only for the moment. So if you can't roll them, cone them, roll the window down, keep zoning. Time don't exist when you coast down.
Guacana pasó, quedó y estuvo a pesar de cicatrices que llevo marcadas. Aún siguen sangrando el daño que hice, las penas que pude pasar.
Oops. So that's another demo. That one we can try live, hopefully. Sorry for that convenience. Yeah, so just a little background. This demo we did for a company that wanted some of these descriptors that they were getting from Spotify. So danceability, happiness, sadness, how relaxed the track is, aggressiveness. And they wanted to basically offload that from the servers and do it on the client side. So they asked us to use some of these Essentia.js models. So we're computing these 5. So we're computing all 5 models, and also like extra regular Essentia algorithms for BPM and key. So we'll load a file. These are different lengths, so it's still a bit not super fast. But so this is like a minute of audio, a bit more than a minute of audio, and it might take a little while to analyze the track. And there we go. So we get our values for the descriptors, and let's have a listen. Right, so I guess we can agree that it's at least a little bit sad and perhaps not very danceable.
So here we can maybe add that, as you remember in the previous demo, we actually had these short chunks on which we could short segments on which we estimated these type of features. So now we basically average across the entire song, the most easy approach. You could probably do better than that.
Yeah, and in fact, we found that as it is right now, and again, please, suggestions, improvements. But we found that in order to be able to analyze like big files or like a minute of audio in a reasonable amount of time, we had to essentially get only a certain percentage of the full audio file. So here, not the full audio track is being analyzed by all the 5 models, but we're taking, I think it's a 20% or 15% of the audio file. So just uniformly get 15% of the file throughout the length of the track, and analyze that instead of the full thing. But yeah, no, that's a couple of the demos that we have. So if you want to carry on, Albin.
Thanks, Jorge. So yeah, I hope you are also able to run it on your system, but maybe not now. You can try it later as well. So let's have a quick look how the code looked like, just for you to get an idea. So this is just a screenshot of a vanilla snippet. On top, you can see I'm importing. It's similar to what we see before during the first session. So we are importing the WebAssembly backend of Essentia. And on the second line, we have some different classes. So it's related to the add-on module we introduced, the Essentia.js model, you can see here. So I'm importing from that build file. So the first class is Essentia TF input extractor. So this is basically computing the feature required for this model. So it will make sure it uses the right parameters and size of the frame and the melt bands, etc. So you don't need to know all those specific details. And then you have a class for example, the first demo you see, it uses new music CNN-based auto-tagging model. So we have a class which exposes interface to access those models. It's called TensorFlow Musician. And on the third line, we are importing TensorFlow.js. And then you can see we have an audio file. So in this case, a URL to an audio file in free sound, creating a web audio API audio context, and also creating instance of an extractor. So it's similar to Essentia API. You just pass the WebAssembly import. And also the second argument is that you are selecting the type of feature extractor. In this case, we have a couple of models which require different type of features. So you can select it while instantiate the class. So once you create the instance, the next thing is to fetch and decode the audio. Again, using the WebAssembly API, you can do that. And the pre-processing step is that most of this model require audio at 16 kilohertz sample rate. And some browsers allow you to do that while you do the mic stream, but some browsers doesn't, so you can manually downsample it. So this method will downsample your buffer. And then the next step is to compute the feature, right? In this case, I'm computing feature for the all audio track. So we have a method called compute framewise, where you give the audio, decoded audio data, and overlapping the hop size. So if you don't provide it, it's optional. It won't do any overlapping frames. So if you want to pass a buffer, we have also a method called compute, which take a single frame of audio and compute the feature. And next slide, you can see we have a path to a model file, which you can download from the repository that Dmitry showed you. So it can be also a URL or a local file in your directory. And then I'm creating an instance of the model, basically passing the global import of TensorFlow.js and path to the model. And then once you create the instance of the class, you have a method called initialize, which is basically a promise for loading the model and warming up. So once the model is loaded, you can call this predict method, which takes the feature input, which we computed at the earlier stage, and it will output the prediction. So simple as that, considering it's happening on a single thread, right? So you can also offload it to different thread and or in a shared memory, etc., to make it work in a real time or like performance required application. So I think Jorge gonna walk us through more later about these technical details. Yeah, I hope you get glimpse of how it is. Maybe I can also walk you through a very simple example on glitch. So you can follow this link on the slide, which will take you to this project. By the way, let me know if anyone has any questions as far, or please feel free to stop me if you have any doubts. So yeah, so you can click this link, and I already have it open, but it's the same project. Okay, I hope you are able to access it. So similar to our old demos, we have the files here on the left hand. So I have a HTML file, a main.javascript, and a CSS, and also I have this downloaded model file here, so that I can use it without hosting it somewhere. So on the index file is normal, so it's the same UI stuff which we deal with in the first session. The important thing, we are importing stuffs using the script tag, the WebAssembly backend, and the add-on module. And then the rest of the stuff are same. We go to the main.js, we have some global, creating audio context. Also, you can here see I'm loading the model, and yeah, selecting some DOM elements. And then we define an analyze function like in our other examples. In this case, we downsample the buffer. So instead of the decoded data, we are taking buffer here. So we are downsampling it, then compute the feature, and initialize the model. So you can also do it globally outside of this function. This is just a very basic example, then you can predict. So if you take the callback of the DOM, so when the onload function, so when the DOM elements are completely loaded, similar to our old example, we instantiate the WebAssembly backend, create the extractor instance, select the button, and attach an event to the click event. Basically, we decode the audio data, SonoSuite API, then call the analyze function, which I explained before, and then just show the results. So this might be a bit glitchy because everything is happening on the main thread. Maybe your screen might be stuck for a few seconds. It's because this is not the best way to use it, because these models require big computational resources, and the best way is to offload it to a worker. Actually, two workers. You can have two workers doing one feature extraction and others doing inference, and you can control it with the main UI. And Jorge is gonna walk us through those details and the real-time example, along with how it's technically implemented, etc.
Yep, let's go for it. So I'll share my screen now. So like Albin said, typically you would want to use at least one worker to offload all this computing to a separate thread. Yeah, I mean, this was like a simple example that we can do in the main thread really quickly. We've seen, and I'm assuming people here know how to use workers or worklets for this sort of example. If not, we can kind of put one together if some of you have like a particular interest and have some doubts in getting that done. But now I'm going to go into the real time, which is basically the mechanisms that we're using for the demo that we just showed, but reduced to its core concepts. So before we go over to Glitch, I just want you to get an idea of what the basic structure of the thing is. We are essentially spawning, so creating from the main thread both an audio worklet. This will be in charge of the feature extraction, which is the prerequisite for using the models. We need to compute some sort of representation of the audio. In this case, it will be a MIR spectrogram. And then we will also be creating a web worker that will actually use the model for inference, right? So this will produce the predictions. In this case, we're using musician again, so these will be genre tags. And so there's only to point out, the basic structure is simple, but just to point out, this kind of dotted line represents the way that we kind of connect one thing to the other, because we need to basically send our features to the model in some way, and those two things are happening on separate places. So that's what this line represents, is that kind of communication. And the way that's done is from the worker, which is the first thing that we create a bidirectional port, okay? And that bidirectional port is then sent to the worklet via the main thread. And well, one end of that bidirectional connection. So each of them has one port of each end of the connection, and that way they can be communicated, and the worklet can send features to the worker. So let's put some code to my explanation so it's a bit more concrete. So again, we'll go over to Glitch. Remember to remix this if you want to fiddle with the code. Yeah, so in this case, all the interface is being simplified. Let's just run it first to see that it works, actually. And we should be seeing the activation. So it will take a while because there's a bunch of things happening in this computer right now, but these are the live activations, and they should change any minute, hopefully. Maybe, yeah, so it's not really getting audio. So let me actually change it to my microphone, even though it doesn't make sense for it to predict on my voice, obviously, but you know, we will see the activations moving, hopefully. So okay, so now they're moving because they're getting some audio. But you know, obviously my voice won't make any sense to these kind of taxonomy. But we see it's changing more or less every second. That should be the rate at which this changes, and I'll explain that in a little bit. So again, simplified UI, so we don't have to worry about that. So again, I won't really go into the HTML, but so the main parts of this, starting from the main file, and going all the way down, because at the top I have all my function definitions. So in here, first thing, you create the audio context, and you set, you know, your event listener on the click of the button. So we will start the whole process. And the process starts when you click the button with creating the worker, right? So create inference worker, which is at the top. This will create our worker with our own JS file, and it will set its own kind of message. So there's a couple of things that we could receive from the worker. The first is the port. This port I just explained here. So we are going to be receiving the connection that we're going to use to connect the audio worklet with the worker, right? So that's the first thing we might expect from the main thread to come from the worker. And the other thing we could be getting from the worker is obviously the predictions of the models, right? So that's the other thing that we will be listening for. And again, simple kind of function that will just basically print this green looking, really nerdy looking thing at the right. And so this create inference worker, it will itself start the audio process. So this will very much like we did with the other real-time examples, we get the microphone stream and we then configure our audio graph, let's say, so our audio data flow. So we first check that the stream is active and the audio context is not off. And then we'll be creating a microphone node. Also, we're creating a gain node because you need to kind of send the audio somewhere. And this will be the custom worklet code. So that's creating the audio worklet. That looks very similar to what we saw earlier with the worklet example. So that's here, create audio processor. We'll get our feature extract processor.js file, which is the other custom code here. We'll go into those in a bit, and it will create the audio worklet. So that way, so back down here, we have all our parts. The only thing we need to do now is first send this port that we've received from the worker, send it to the worklet. So now they will be connected. So that's the worker to worklet port. Okay. So we do that, we finish connecting the nodes, and all is good. So first of all, this port, where did we get that from? Remember, we're listening on the worker itself. So right here, one of the things we're listening for is some sort of port from the worker. So we go to inferenceworker.js. We will see down at the bottom, we're creating message channel and a port and sending that to the main thread. So tada, we've connected the two things. Just as a note, the reason I'm communicating these two bits with the post message interface is just because it's quite slow. So this features are going to the model every second. It's not super fast like in other real-time audio applications. But in those cases, you might want to use something like a shared array buffer or some sort of shared memory between the two threads. Okay. And yeah, the rest of the code here is, importing Essentia like we've done before. In this case, we're also importing TensorFlow.js. And we have our URL to the model, which like in Albin's example, it's here in its own folder. That's the musician model. We instantiate the algorithm that uses that model that can kind of recognize the inputs from it. And we have a kind of function to load the model. So we call it initialize method. And then the function that will actually call the model predict. And then it will kind of manipulate the predictions in such a way that we know basically what each of the activations mean. So that's why we have these tags here. So that you can get from our main repository of the models, which is here in models. So if you want to come here and let's say you want to use musician, so that's an auto tagging model. That would be the data set that they're trained on. So this is trained on million song data set. And here in its JSON file, you will be able to find this kind of metadata. So here you have a classes attribute, and this is the exact array that I'm using that tells you basically that the first activation from the model corresponds to rock, and the second to pop, and the third to alternative, and so on. So that way we know that this activation corresponds to rock, right? And that's all that's happening in the inference worker. So it's relatively simple. Now this works as we can see here, it's listening on this port, which is the shared port between, or like the shared communication between the worker and the worklet. It's listening for audio features, okay? So it just listens for the features, and when it gets them, it calls model predict. But we need to get those features from somewhere. So remember, we have this microphone stream from the user, and that's connected via typical web audio nodes into this audio worklet. Now, this audio worklet example is a bit more convoluted for me, but I'm sure there's people here that have used much more complicated worklets. So in typical fashion, we import Essentia. In this case, it's an ES6 type of import with its WASM backend. And in this case, we're using the Essentia.js model package instead of the core package. Again, this will seem familiar from earlier. So we're not using, we can't use with this model the default audio worklet 128 samples. This model in particular takes 512. So we need to use some sort of ring buffer that will accumulate. Okay, and I won't go more into that. But yeah, it's the same as we did before. We have to accumulate up to 512 samples. And those get accumulated in this variable here called features and spectrum. So we're right down here in the process function. So we have instantiated our extractor, which is this method here. So Essentia TF import extractor. Okay, that's from this Essentia.js models package. It uses the WASM backend as well, but this will compute the specific, the specific features that this model needs. If we tell it that it's a musician model, it knows that it has to compute. In this case, it will use 512 samples for the features, and it will give us mailbands, 96 mailbands, right? 96 bins. So that's the input representation that the model is trained on and designed for. And the rest is just using the extractor. The extractor has a compute method. And so given frame data, so remember we've accumulated, and this is our buffer of size 512 in this case. We gave it to the compute, and we get its mail spectrum, and we push it to the features. Now, I'm pushing to this kind of, this is a matrix, effectively, is because the model has a receptive field, right? So it will see, in this case, 3 seconds of audio. But in this case, since it's a real-time example, and that's what's happening on the demo that we showed earlier, we want to give a feeling, more of a feeling of real-time. We don't want the user to wait 3 seconds until we get the next prediction. So all I did was introduce some sort of overlap on this matrix as well. So we spoke about overlap earlier with typical signal processing. This is just implementing a sort of overlap on this matrix itself, and that's what this little class up here is doing. Is the patch hop. So patch is this, basically it's a collection of mailband frames that we're sending to the model for input. So this is just making sure that every second I'm sending the patch to the model. So the model essentially will see every second, it will see like 2/3 of it because it has a receptive field of 3 seconds. So it will 2 seconds of it will have already seen, and only 1/3 of it, 1 second, will be new every time. So that's what I consider overlap, okay, or hop, right? And that's it, I think, because otherwise I will take up too much time. Does anyone have any questions? Want to poke at my code? Please feel free to do that. I'm sure this can be made more efficient.
Just a note that we try to make it as simple as we can, or because there are better ways to do it, and probably many people in this community can also give us some input on making it more efficient. But we want to have a very simple example that works so that everyone can go through it.
Yeah, so that was a real-time multi-tagging example. As Abby said, this is as simple as I could make it. I mean, bear in mind, this is running deep learning models in real time.
It's okay. It's nice
hard to make it. It's hard to make it super simple.
What puzzles a little bit to me, because I don't know how this thing works, is this thing about overlapping. I got lost in the first example of real-time with a ring buffer before, and then with this thing too. But maybe this is too complex to.
No, I mean, so overlap. Let's have a look at some images, and maybe you can see. So I mean, this is a typical image. So if this would be our main, I'll make it bigger maybe.
Okay. Yes. No.
Oops. Well, I mean, I guess you guys can see this, right?
Mm-hmm.
So if this was our input signal and we've cut it into frames, or we're working in real time, so we're getting one of these blocks every time. And I'm not sure this is the best, but you get the idea that like this, I mean, that would be what's labeled here as Y would be a frame, and the next frame would have some of the contents of the previous frame basically in its first part, right? So this part right here would be the overlap. That's what I mean with overlap, right? The signal. So each frame doesn't have totally new content; it has partly new content. And this overlap has reasons for being in the digital signal processing world. It eases a lot of spectral processes and reduces noise in those processes. And I won't get into this because I'm sure there's many people in the audience that can explain that a lot better than I can do. But does that help, Danny, with the?
Yeah, it is. Thank you.
Great. Yeah. So is that back to you, Albin? Or no, maybe Luis? We're doing the industrial stuff, unless anyone has any more questions. But
we also have a QA session at the end.
Oh, yeah. So Luis, take it away.
Okay. Wait, sorry. Damn, I forgot to put the share audio. Okay, now. Can you see the screen?
Yes.
Cool. So, well, let's go to the most difficult part of the. It's a joke. This is going to be actually very simple compared to what the examples that we've shown before. I'm just going to talk about an industrial application. Just to put it a little bit in context, as I mentioned at the beginning, I'm working in SonoSuite. I've been working there for 4 years, and what we do in SonoSuite is a web platform for digital music distribution that we sell to small companies like small labels, and then these small labels and their artists can upload their music into our platform, and then we manage for them the distribution to digital channels like Spotify and iTunes and this kind of music providers. One of the important things for us once they upload the music is to ensure that the quality of the music is good. So they don't have, when I mean quality, I don't mean if we like the music or not. I mean if the audio file has any kind of issue that we should avoid before sending it to the digital platforms. So in SonoSuite, we started 3 years ago collaborating with the MTG, and one of the first projects that we did, that actually we did it with Dmitry and Pablo, that is also here in the room, is this detection of audio problems. We studied and developed these algorithms to detect audio problems that are very typical in the audios, in the files that we receive. Problems like incorrect margins and phase stereo problems, all the kind of audio artifacts like distortions and noises and all these things. And actually we all these algorithms are inside Essentia, and we published and presented a paper talking about all this in the Audio Engineering Society convention in 2019. So as I was mentioning, one of the important things for us is to detect these audio problems before sending the music. And how we do it right now is with people in the quality control department, and they listen to the music to detect if there are any problems. So what we wanted with this project is to be able to detect these problems and show them to these people that is listening to the music, so they can go, instead of listening to the whole track to see if there is anything, we can tell them, we think in this part of the music there is a problem, and so then can decide, and if they have to contact with the artist to change it, then they do. That's the beginning of the history, and in this case we were using Essentia native, so this process is done in the server. But then we imagined that if we could use these algorithms in the client, we could make this process, and when the artist is uploading the song, so we can directly tell them that their music has any kind of issue, instead of having to send the music to the server, then the QC people see it, and then they get in contact. We can directly tell them this music has this kind of problem, so maybe you need to improve this or avoid that, and then you can upload it again. And that's why we also started collaborating in the making of Essentia.js. To show you this example also, there's another thing that it's important to explain a little. Actually, Albin and Jorge have mentioned this before, and this custom extractor. There's mainly two reasons to have these custom extractors, or to make them, I mean. One of them is to improve the performance of Essentia, of the algorithms of Essentia in JavaScript, because in this way, instead of having to do the whole pipeline, as Jorge showed you, using the algorithms in JS and using the output of one algorithm to send it to the next one in JS, you can do that directly in C++ and compile it, and then in JavaScript you only need to call one function to execute everything, and that improves the performance. Also, as we mentioned, we are not yet ready to launch Essentia in production. We are still working on it, and there are some algorithms that are not yet fully working in Essentia, and this is the case in my project. There is one algorithm that it's not working, so I needed to create a custom extractor to use it. Here you have 3 links to an example of the files that you need to create in C++ to do a custom extractor. You can see that later, if you go to these links, that it's very easy code. You only need to do something very easy, and then just use the make file that we provide, or the Docker image to compile it, and it's very simple. Just to show an example of how the compute function would work, and how I'm here for this saturation detector, I'm just only creating like a pipeline with just 2 algorithms, which are the frame cutter and the saturation detector. And here I'm connecting the inputs and the outputs in C++, and then we have a while that just runs the algorithms for the whole track, and at the end we return the results. So if we go to this example, as always, you can remix it to make it your own and to play around. Here we've done some, this is just like a prototype of what we are working on, as I mentioned, to allow, well, to do the analysis of the algorithms in the client in instead of making it in the server when the audio, when someone uploads the music. So here I'm just using two algorithms: saturation, which is the custom extractor, and stop cut, which is part of Essentia.js. And it's a very simple application that where we click here, it loads the audio, it draws the waveform, and as you could see, it takes a little to paint this zone in red because it's making the calculations, and then it marks in red that here we have saturation, as well as in here. Hope you can see. And at the end, we have a cut. So just to show you that what we find is true and we can perceive it, I'm going to play. You'll see like here we have like a little click, and then in this zone we have saturation, and at the end it's going to cut. Be careful with the volume because in this saturation part the volume increases, so maybe you have to remove the headphones, or I don't know. No, can you hear it?
Yes, we can hear it fine.
Una sonrisa no oculta nada. Hey, caras vemos, vidas no sabemos. Pues, el demonia, los más groseros, el Aldair, FS Pro, wow. Una sonrisa no oculta nada. Y desde no te abre la mirada. Una vida mierda, cruel, despiadada. En este mundo no vale nada. Una sonrisa no oculta nada. Y desde no te abre la mirada. Mi vida se consume como un toque. Pasé por tanto, así que no esperes que me equivoque.
Yeah, so
is this a real example, Luis,
yes,
from someone uploaded this track?
Yes, I'm not going to say the artist, but yes.
I've always thought that this track you modified it like to like show this. It's real.
It's real.
Wow.
And it's not the worst thing that we find. I mean, just as a joke, but I don't know if all of you know this show for kids called Teletubbies. It's just a show for kids. So we found a track that in the middle of the track had like a little bit of the Teletubbies talking, and then continued the track. So yeah, you can find very weird things. So yeah, well, just to show you a little bit the code that works with the Essentia. I mean, most of the code here is just to because I have this canvas and I draw the waveform and everything in this canvas, but the important part for Essentia is just this load function where we are loading the Essentia, the standard Essentia.js, and here we are loading the custom extractor in kind of the same way. Just in this case, we need this frame size and hop size to send to the saturation detector extractor. And once the Essentia is loaded, we call this compute start stop cut. That it executes the algorithm, and then we just can paint the results. And the same thing when we load the custom extractor, we call compute saturation. That calls, in this case, these two functions that I made in the custom extractor, and the same idea. Once it's calculated, we can draw in the canvas the results. It's just a very simple application, but in our case, it can be a very significant improvement for the whole process of uploading the audio files, knowing if they are okay, and if not, telling the artist. So yeah, that would be it from my side.